All right, so let's get started. So we're going to be talking some more about linear programs today, and depending on how long that takes, we'll get to duality either today or next time. So just for review, linear programs, besides being the coolest problem on the face of the planet, are described as a set of n variables with m linear equalities or inequality constraints. If we have constants, A, which is an m by n matrix, B, which is an m vector, C is an n vector, and X is a vector of variables, right? Then we can have the inequality form linear program, which is to minimize or maximize C transpose X, so a linear function of our variables, subject to linear inequality constraints, AX is less than or equal to B. And in this case, we want to have m bigger than or equal to n, or we can. We can. We could really have fewer inequalities, but then with high probability, you're going to be able to just go off into nowhere. Or we can have standard form, which is equality constraints. And so here there are fewer constraints than variables, but all of our variables are required to be bigger than or equal to 0. So here's the one that we've been working with for the past day or so. Right, maximize 2x plus 3y, subject to x plus y less than 4, and a whole bunch of other constraints like that. All right, so that's a linear program. Sound familiar from last time? Okay, good. What have we learned about linear programs? Well, they have a polyhedral feasible set, meaning that if the feasible set is non-empty, it's the intersection of a finite number of half spaces. If it's non-empty, well, then the opposite is if it's empty, then the problem's infeasible. You remember the unhappy ball and the getting squished between two constraints from last time. Or it could be unbounded, right? So we could have a polyhedron with infinite extent as well. And if the objective vector is pointing in that direction, that's when we lose our ball, right? The ball keeps rolling off into infinity. The optimum of a linear program, there's always a vertex that is an optimum, if there is any optimum at all. In other words, if it's feasible and bounded. We talked about how to transform linear programs. So for example, we can take inequality constraints and swap their sign by negating them. We can take equality constraints and turn them into inequalities by having two opposing inequalities, right? If you're this side of the half space and that side of the half space, then you must be on the line. We learned how to use slack variables to get rid of inequalities and to change free variables to bounded variables and vice versa. All right. So we also talked about the Tableau representation of linear programs. So Tableau just means table. I don't know why they use the fancy word, but it's tradition. So here's an example Tableau. It corresponds to our favorite linear program. So here, this is the A matrix, right? This is the B vector here, right? So the A matrix is here, the B vector is here, and then this here is minus C, right? And you can incorporate the objective into the Tableau by having an extra variable z that's constrained to equal the objective. We talked about how to do row operations on a Tableau to get an equivalent Tableau, right? So anytime you replace a row by a linear combination of other rows, as long as you don't lose the linear independence, then you've got an equivalent set of equality constraints. And that let us define what a basis is. A basis is basically when we use row operations to make some m by m block of a Tableau equal to the identity matrix, right? So here u, v, w, and z are our basic variables, and we've made their block equal to the identity matrix. And we talked about how bases more or less correspond to corners in the sense that, okay, if we set all of these non-basic variables to 0, then we can just read off the values of the basic variables, right? So u here is 4. right? Because we set these guys to 0, and so we constrain u to equal 4 directly. Okay? And the reason I say more or less is that, well, it can happen that a basis results in something infeasible. So it's a corner, an intersection of the appropriate number of constraints, but it's outside the feasible region. And it can also happen, we'll see later today, that two different bases correspond to the same physical corner. And that's called degeneracy, and we'll get into that in more detail later. All right. But the way to think about it here is that if we set all of these non-basic variables to 0, then we have exactly the same number of variables as we do constraints. And so it's exactly the right number to get yourself down to a 0 face, which is a corner, assuming it's feasible. All right. So any questions about the review? All right. I must have been very clear last time. Okay. Oh, go ahead.
What do you mean by row operations can make set of constraints not linear?
So if I were to take one constraint and replace it by 3 times another constraint, then I would lose linear independence, right? So I would basically, if I just, like if I replace a constraint by some linear combination that doesn't contain any weight on that constraint itself, then that constraint has essentially vanished, right? And there are other similar things that you can do to lose linear independence. All right? Okay. So there was a question yesterday about the relationship between standard form and inequality form. And we determined in class that basically inequality form is a projection of standard form. And I wanted to get basically a nice MATLAB drawn picture instead of the hand waving that I was doing yesterday, because I think it's kind of a cool intuition. So here is a nice linear program. We have 3 variables, x, y, and z, 3 variables so that we can sketch it. And we have a constraint, for example, 3x plus y plus 2z is equal to 5, right? And so I think this one is the blue constraint, and this one is the green constraint. So I just did a plot of what the 2 constraints look like, and then their intersection here, this line, that's the feasible region, right? And I've also got x, y, and z all have to be bigger than or equal to 0. All right, so this picture makes sense? All right, so this is now a linear program in standard form, and it has 3 variables and 2 constraints. And so I can, there are 3 choose 2, which is to say 3 different bases, right? I can pick x and y to be basic variables, x and z, or y and z, right? And so with those 3 bases, well, here, I've just taken those 3 bases and done the appropriate row operations to make them to make their corresponding submatrix be the identity, right? So here x and y are the basis, here x and z are the basis, and here y and z are the basis. And I had MATLAB do it, so hopefully MATLAB got it right. And I can take each one of these and I can interpret it as a projection of the feasible region. So let's take a look at this one here, right? If I make x and z be my basic variables, then y is my non-basic variable, right? And I can, if I think of these guys as slacks, then y is the only variable that's remaining, and so I can think of each of these constraints as only a constraint on y, right? And so this first one, right, is basically 5 times y plus a slack variable is equal to 5, right? So 5y is less than or equal to 5, or y is less than or equal to 1, right, which is this constraint here. And then because this element is negative, right, I have minus 7y is less than or equal to minus 5, right, or 7y is greater than or equal to 5, or y is bigger than 5/7, right? And so that's this constraint right here. Okay? And if you look here, what I've done is I've rotated the picture from the last slide so that you can see the constraints on, this is the y-axis here, and this is the x-axis here, right? So this is x and y, right? And so you can see here's the feasible region, and if you project it down to this axis, it does look more or less like we're between 1 here and 5/7 here, right? So we are actually seeing a projection of this higher dimensional feasible region onto the remaining variables, the ones that aren't slacks in this particular representation. All right? And then you can see the same thing with x here, right, which is this one here. Here we have two constraints that are the same sign, so one of them is redundant, and so we just have x is bigger than or equal to 0 here, and less than or equal to 10/7. Okay. So the picture makes sense to everybody? Cool. All right, so I just wanted to draw that picture because I thought it certainly helped me get a better understanding of what was going on. All right, so I've been extolling the virtues of bases. What happens if we can't pick a basis? So there's a couple of reasons we might not be able to do it, right? A basis, if there are m constraints, a basis is a set of m variables whose columns are linearly independent, right? And if our matrix A, if our constraint matrix doesn't have full row rank, well, there's no way we're going to be able to pick m linearly independent columns, right? So we won't be able to get a basis. And an example of that is something like this, right? 3x plus 2y plus z is equal to 3. 6x plus 4y plus 2z is equal to 6, right? So this constraint is just twice that constraint, right? And so, for example, if I pick this column and this column, right, well, this column is 3/2 of this column, right? So they're not linearly independent. And no matter what pair of columns I pick, I'm not going to be able to get linearly independent ones. So what do we do in this case? Any thoughts? Here, throw one away from one of the TAs. So yeah, that's exactly right. So this constraint is completely redundant with this constraint, so let's just throw it away. And now we have, well, one constraint, and so each column is just a single number, and all of the non-zero ones are linearly independent, and so we're good, right? If this had been 7, right, well, we could still throw this away and solve it using the remaining basis, and then we could check our solution, and we'd find out that it didn't satisfy this constraint, right? And so that's still an algorithm for solving it, right? So basically, if we have too many linearly dependent constraints, then either we satisfy the last one by accident if we satisfy all of the other ones, or we don't satisfy it at all and there's no way we can satisfy it, right? So here, if we change it to 7, it's like two parallel lines, right? There'll be no intersection. Okay. So, so the algorithm then is just throw away non-independent rows while preserving the rank of the matrix, right? You don't want to throw away something that reduces the rank of your constraint matrix. But throw away rows until we do get linear independence, then solve it that way with the reduced set of rows, and then once you're done, you have to check the constraints you threw away. And either you satisfy them and you have a solution, or you don't satisfy them and it wasn't possible to get a solution. Okay. Another reason could be if we have fewer variables than constraints, right? So that means that in standard form, our constraint matrix is taller than it is wide. And we can't even pick enough columns to make a square matrix, much less a linearly independent one, a full rank one. So an example of that would be something like this. So if we had the constraints x plus y equals 2, x equals 1, y equals 1, right? So what that looks like here, right, we have our axes, we have x plus y equals 2 like that, right? That's 2, that's 2. Then we have 1, zoop, like that. We have 1 like that, right? And then this is our feasible region right here. Okay, so what this corresponds to is we have redundant constraints, again, and we can just toss one of them, right? So for example, well, if we toss this one, right, it makes it very easy to solve. X equals 1, y equals 1, and then we can check that x plus y does in fact equal 2. And if it had been x plus y, the same thing equals 3, well, we solve here, we check, and it fails to satisfy it, and then we know, right, if it was like this, right? We'd know that it was impossible to satisfy, and we'd be done again. Okay? So that means that, go ahead.
While we are doing the Gaussian
right. So a good way to do it is just ignore this possibility, start doing Gaussian elimination, and while you're doing Gaussian elimination, you notice a singularity, and then you fix it. And you pretend that you weren't using that row from the beginning. And that's just fine. I was just thinking, from the beginning, we could have thrown the row away if we check. But you're right. The actual algorithm would be to check it while you're doing the Gaussian elimination. All right? So that means that we can assume from the start that we have at least as many variables as constraints, and our constraint matrix has full row rank. All of the rows are linearly independent. All right? Because we can just drop rows maintaining rank until it's true. And with this assumption, we have what's called a non-singular standard form linear program. Right? And so for the algorithms, we're just going to assume that that's the case. And that's going to make it a lot easier to describe the algorithms. Okay? So we now have our first algorithm for solving linear programs. Right? We put it in non-singular standard form. We iterate through all subsets of n variables, right? So if we have m constraints, how many subsets of n variables are there? Right? Sorry, all subsets of, that should be of the m variables out of the n, to be perfectly clear, right? That means since we have m constraints, and so we'll have n choose m such subsets, right? A lot, but we can iterate through them. And then we're going to check each one for being a full rank, in other words, being a basis, and for feasibility, which we check by making that block of the Tableau equal to the identity matrix, and then looking at the right-hand side, right? If the right-hand side vector is all positive, non-negative, then that's a feasible basis, right? So this takes... you can do both of these by factoring that block of your Tableau, right? So you can do these in O of n cubed. Sorry, O of not n, but m cubed. Right? And if it passes both tests, you can compute its objective value, right? The dot product with the objective vector. And you save the best one so far, and once you're done with everything, you return it, right? So this is an algorithm. It takes O of m cubed times n choose m, right? So not a very fast algorithm, but in fact it is an algorithm, and we now have an algorithm for solving linear programs. And actually, for a long time, this was essentially the best known algorithm. Right? People actually thought that this was, you could be smarter about the search, but you were, in the worst case, going to have to do essentially this. All right. So now we're going to go to an actual algorithm that people would want to use in practice. But it's kind of nice to know that this one exists, right? It sort of tells you that linear programs are effectively a combinatorial problem, right? Without this algorithm, you might think that it's a continuous optimization problem, and you have to check essentially every of the uncountably many vectors that could be in the feasible region. But here, at least, we've reduced it to a finitely solvable problem. So that's nice. All right. So the naive algorithm was to enumerate every basis. The smarter algorithm is based on the intuition maybe bases that are kind of like good bases are also good bases, right? So what do I mean by a neighbor? Well, I'll talk about that in a couple of slides. But the simplex algorithm, which is probably the most famous algorithm for solving linear programs, is you start at some basis and repeatedly move to a neighboring basis to try and get a better objective. Okay? And so let's continue to assume a non-singular standard form linear program and talk about what it means to be neighboring bases. So Remember, a basis is a set of variables, and it's a set of m of them if there are m constraints. And so if they share all but one variable, they're going to be neighbors, right? So here on the cube, right, I can say that if x, y, z, u, v, and w are all bigger than 1, and x and u sum to 1, y and v sum to 1, and z and w sum to 1, then x, y, and z are all in a cube, right? And so if I choose the basis x, y, z, right, and I set all of the non-basic variables to 0, right, well, then x, y, and z are all equal to 1. I'm up at this corner. If I now, let's say I swap z out of the basis, and it turns out that w is going to be the thing that comes into the basis, right, then x and y are still 1, but now z is 0 and w is 1, right? So we're going to move down to here, right? And so this geometric intuition, we just moved along an edge where we're varying z, and we got to another basis where z is out of the basis and w is in the basis, right? That intuition is exactly what we want neighboring bases to incorporate. So sort of in the usual case, neighboring bases correspond to neighboring vertices, zero faces of our feasible region, right? And what we just did, so take one variable out of the basis and put another one in, move to a neighboring basis. That's called pivoting. And in this particular case, z was the exiting variable. It came out of our basis. And w was the entering variable. It went into our basis. Okay? All right. So let's try and solve our favorite linear program by moving from basis to basis. So let's say that our initial basis is this one, right, where all of the slack variables are in the basis, right? And so to get to a corner, we'll set x and y equal 0, and we'll read off the values of s, t, u, v, and z, right? And so, well, that corresponds to this corner, right, because x and y are what we're plotting, right? So here's x and here is y. And these fact that these are all positive means that we're feasible, right? All of these constraints up here are loose, and we're at a corner of the feasible region. Okay? So, s, t, u, v, and z are in our basis. X and y are not. If we want to move to a neighboring basis, we're going to have to make either x or y be the entering variable, right? So let's consider taking y and increasing it a little bit away from 0, right? So we're going to go like that, okay? So what's going to happen? Well, so when y goes up by delta, right, and we're keeping x at 0, well, there's a constraint between y and s saying that they have to sum to 4, right? So if we have y plus equal delta, right, then we'll have that s has to decrease by delta in order to keep this constraint feasible, right? Here, if y goes up by delta, well, then t has to go down by 5 delta, right? So we have t minus equal 5 delta, right? And so forth, right? So u minus equal 2 delta, right? And here, well, here y going up by delta doesn't actually move v at all, right? So v, no change. And then z, our objective, right? So y is going up by delta. That means that we go down by 3 delta here, and z has to increase by 3 delta, right? And since we're trying to maximize z here, that's a good thing, right? So it seems like a nice thing to let y enter the basis. All right, we've confirmed that. How far can we increase y while maintaining feasibility, right? That's the next question. So what we're going to try and do is increase y as much as possible, right? And so, well, you can see from the picture that we're going to wind up here, right? But let's derive that. Let's look at how we can look at the Tableau and figure that out. So if we look at this row here, right, to get s equals 0, right, we'll have y equals 4, right? That's way up off the top here, right? In order to get t equal to 0, right? So this is when we're gonna lose feasibility is when one of these right-hand side values would drop to 0, right? Or I'm sorry, when one of these slack variables would drop to 0 based on not exceeding the right-hand side. So here, if we look at t, right, if we make y equal to 12 over 5, right, then, well, t will have to go up by, t is currently equal to 12, y will go up by 5 times 12 over 5 is 12, and so t will have to go down by 12, right? So we can make y equal to 12 over 5, right? Which is something smaller here. It's this point here, right? Here we can make y, whoops, that's actually not true. It's actually this point right here, 2.4. For this row, for the u row, right, if y goes up to 5 halves, then u will go down to 0. Right, y equals 5 halves. And then here, again, there's no limit based on v, right? We're never going to make it infeasible by changing y. So the smallest of these things is 12/5, 2.4, right? And so that's what's going to wind up limiting our increase. And what that means is that if we increase y to 12/5, we've decreased t to 0, right? And that means that we can let it leave our basis, right? Because we want to set all of the non-basic variables to 0. And so now if we have y enter, we know that t will leave, right? And we have a new basis, right? So it's now ys uvz. Okay? And like I said, we've moved to this point by moving y up to 12/5. And then this constraint here, right, this is the constraint that t belongs to, and that constraint became tight. Okay. So an interesting point is to note that this basis still has to be a basis, right? It still has to be full rank because t was a function of y, holding the other variables fixed, which means that we can either have t or y in the basis and still have it be linearly independent. All right, so we just did our first pivot. Woohoo! Okay, so we now moved to the basis ys u, v, and z. So I happen to have prepared on the next slide the tableau that corresponds to ys, u, v, and z. Okay, and I just had MATLAB do it, but if you wanted to do it, what you would do is you would use this. So let's go back to the previous slide. You would use the t row to eliminate y from all of the other constraints, right? And that would cause fill-in in t's row, and y would only have one non-zero entry in its, cause fill-in in t's column, and y would only have one other non-zero entry in its column. All right, so here's what we got. And we're currently sitting at this vertex, right? That's what we calculated at the previous slide. And now let's think about, so we now have x and t in our basis, right? We improved our objective value, right? We moved in the direction of the objective vector, which was like that. Let's think about what would happen if we added each of x and t to our basis, right? So t just came out of our basis, and it helped us to take t out of the basis. So hopefully it's not going to help us to put t back into the basis. But let's see how we can see that, right? So if we were to increase t, then we would wind up having to decrease. Well, so if we were to increase t, then we take a look at this entry in the objective row, right? And that says that, well, the objective is going to get worse at a rate of 0.6 for every unit that we increase t, right? And so we don't want to increase t, right? So these entries in this objective row, right, are called reduced costs. And the reason is that they basically tell you which entries, which variables it's worth putting into your basis, right? It tells you the cost for changing directly that variable. Okay. So, so those are useful to have around. You'll notice that the sign of the reduced cost on x is the opposite sign. So that makes us think that adding x to our basis will improve things. So let's go ahead and add x to our basis, right? And if we take a look at how much we increase x, right? So increasing x means we're going to move that way, and it's probably not going to surprise anybody to know that it means we're going to move along this constraint here, right? So let's see. If we look at the y row, right? So if we increase x by 1, then we have to decrease y at a rate of 0.4, right? And that rate of 0.4, well, how long are we going to be able to do that? Well, we'll be able to do that until y hits 0, right? And it starts off at 2.4, and it's going down at a rate of 0.4. So it'll be, well, the distance we can increase x is going to be 2.4 over 0.4, right? Which is equal to 6, right? So we'll be able to increase x as far as 6 before we run into infeasibility according to this constraint, right? Same thing, right? If we look here, it's going up. If we increase x, then s will have to decrease at a rate of 0.6 per unit of x. And it starts at 1.6, right? So it'll be 1.6 over 0.6, which is equal to 2 2/3, right? Here, 0.2, 0.2, right? That's, well, 1. I'm not even going to write it out. And then here, 1 and 4. So 4 over 1 is 4. Right? And so the tightest one is going to be, whoops, not that one, this one, right? And so we can increase x as far as 1, right, which gets us to this next corner right here, where the x value is 1. And it's going to cause this guy, right, u, to drop out of the basis, right? So our basis was y, s, u, v, and z. And we have x in, and u is going to go out. Okay? And so what we just did over here, this is called a ratio test, right? We're taking the right-hand side and dividing it by the column corresponding to the entering variable. And it tells us what's going to be the tightest constraint, right? So we just take the tightest one, and that's the one that's going to be leaving, exiting the basis. All right? So now our basis is going to be x, y, s, v, and z, right? And it's going to correspond to this point, and it improves our objective, right? We got to increase x by 1, and so we improved our objective by 0.8. Okay? So we're at this point right now, right? And our this is our basis, x, y, x, v, and z. And I called on MATLAB again to make the appropriate tableau, right? And I'm not going to do the full computation, but what we notice is that, so unlike before, right, t is going to help us and u is going to hurt us, which is kind of interesting, right? So we're at an objective value of 8 now, and t is going to increase that at a rate of 1, and u would decrease that at a rate of 4. And that's kind of interesting because we took t out of our basis before, but now we're putting it back in, right? And so it's not like we can throw something away once it leaves our basis. We may wind up having to put it back in, right? What will wind up happening is, well, if we do the ratio test, right, we go through and we divide the right-hand side by the entries here, what will wind up being tightest is this row, which has tells us we can increase t by 1, and s will go out, right? So this will be in, s will go out, right? And it will wind up putting us at this point right here. Okay. So if we now look at the resulting basis, right? So now our basis is x, y, t, v, and z, right? And we can read off here x and y are 3 and 1, right? So I just claimed on the previous slide that it put us here, but after putting us in this appropriate form, putting the tableau in the form to illustrate that this is the basis, we can read off x and y, and we are in fact there. And now if you look at s and u, so we're at an objective value of 9 right now. If we look at s and u, both of them would hurt if we put them into our tableau. And so that means that we're done, right? Which is, well, since the objective vector is that way, we've moved as far as we can in that direction, right? So that's the simplex algorithm in pictures, okay? So, any questions on simplex? Yeah. Right, so the objective function is linear, and we're going to wind up monotonically increasing the objective with every step of the simplex algorithm. Right? And geometrically, if you think about it, you imagine that you're at some corner of the feasible region. There's always going to be some edge you can, either you're optimal, in which case all of the edges point away from the direction of the objective, or there's going to be some edge leaving your current corner that you can follow to increase your objective, right? So, yeah, basically that's the intuition for why the simplex algorithm works. Okay? Yeah? How does looking at S and U do what? Right, so I'm looking at the reduced costs, these guys here, and since they're both bigger than 0, that means that increasing S is going to decrease Z, right? And Z is our objective, and so we don't want to decrease it. So that means we don't want to go anywhere. Yeah?
So you have multiple negative values in the objective row. You select the one which is the higher rate?
That is an excellent question. Nobody knows the answer to it. So the question was, if we have multiple negative rows, multiple negative reduced costs in the objective row, which one do we select? The obvious answer would be to select the largest one, right? The most negative one that improves you at the fastest rate. It turns out that there have been dozens, if not hundreds, of recipes that people have proposed for selecting which one to do. And for every single one of them, there's a counterexample showing that that leads to an exponential time algorithm. you'll be looking at one of these exponential time algorithms in your homework 3. It's called the Klee-Minty cube because of Klee and Minty who came up with it, and cube because, well, it's not actually a cube. So I don't know why they called it that.
So maybe the ability is to select at random?
Right. It would be nice if you could show that in expectation that led to a polytime algorithm. Nobody's been able to show that. The closest that people have been able to do, there's a quite recent result by Spielman and Tang, which I'm actually going to mention a little bit later, but let's mention it now. So what it says is that if you use a particular rule for picking the pivot, which is called Bland's rule, and if you at the very beginning perturb your linear program by adding random noise to some of the entries, then with probability 1, it'll be a polynomial time run. Now, of course, this means you're solving a different linear program than somebody gave you. So it's maybe small consolation to know that you solved it in polynomial time. But that's the best result that anybody's been able to give, right? And they show actually for quite small perturbations that this is still true. Yeah?
So for randomized rules, as of like 2 years ago.
High-lower bounds meaning you know that they're not going to be efficient?
Sub-exponential, so I think super polynomial.
Okay. So we have a possible result that the randomized pivot rule, picking randomly among feasible pivots, is going to be super polynomial.
2 to the omega
2 to the omega
n.
n to the alpha for some alpha less than 1?
Alpha greater than 0.
Alpha greater than 0, yeah. Okay. Okay, so that's the latest. Yeah, so simplex, another reason simplex is a cool algorithm is it's really kind of a simple algorithm, right? I basically showed you all of it in 5 slides. And yet it's really, really tough to analyze, right? It was proposed 60 years ago, something like that? 47? Okay. 47 years ago.
No, 1947.
Oh, 1947. Okay. So that is pretty close to 60, right? It's 65, yes. So 65 years ago, people have been trying to analyze it ever since, and this is the best that we have, right? The other thing that's kind of cool is that people observe that in practice, simplex is really, really efficient, right? And nobody has been able to prove it. The closest thing that has come to a proof is the Spielman and Tang result, which is that essentially most linear programs in any region of the space are efficiently solved by simplex, right? Which is not the same as the linear program that somebody is paying you a lot of money to solve is easy to solve, but at least some nearby problem that you're not going to get lots of money to solve is efficiently solvable. Yeah.
There's some indication about which cases for all
No, once you pick the non-basic variable that you want to enter, the ratio test tells you which basic variable has to leave, right? Because you keep increasing it, and you increase it only as far as you can while maintaining feasibility, and whichever constraint becomes tight first, that constraint is... Oh, you're right. It is possible in case of degeneracy for 2 constraints to become tight, and yes, in that case, you have the choice about which one leaves as well. Okay. All right, so that's simplex. I swept a couple of issues under the rug, so that's what's going to be the rest of the lecture, what I've swept under the rug so far. So I assumed at the start that we started with a feasible basic solution. And in fact, it was trivial to find one because the initial basis, we just started, it was given to us in some particular form where a basis was chosen for us, and that basis was feasible. And it's not so easy necessarily in general. Okay? So how do we find our initial basis? Probably the most popular method is what's called the big M method. You'll see why it's called that in a sec. So here I have a linear program where the initial basis here is not feasible, right? Well, so what do I do? I'm going to add a new variable, which I'll call q, right? And it's going to appear, so there's one violated constraint, right? That's this one, right? And it corresponds to this negative entry in the right-hand side, right? And so I'll put q here. So q is also greater than or equal to 0. I'll put q here with coefficient -1, right? And so now, if I were to increase q, right, then that would wind up making this constraint feasible, right? So that's kind of cool. Of course, there really isn't a variable q, right? So I don't actually want it in my final solution. So what I'm going to do is I'm going to penalize it in the objective, right? So I'll take minus some huge number, capital M, times q, hence the name big M, right? And hopefully if I pick M big enough, then I'm going to set q equal to 0 in the final solution, which will mean that I'll be feasible for the original program as well, right? And it turns out that there's a recipe for calculating what M is big enough, but it's not very enlightening, so I'm not going to go through it here. All right, so this is a recipe for how to make it feasible, but the current basis still isn't feasible. So what do I do? I'm going to negate this row. Plus, right? And now q is in the basis, right? This last slack is out of the basis because it has a coefficient that's not 1. And the right-hand side became positive because I negated it, right? And so now I've gotten myself to a feasible basis. The basis is now x, y, and q, right? Sorry, the basis is now the non-basic variables are still the same, x and y. The basis is now the first 3 slacks and q. And I'm good to go. I can start simplex from here. Okay. And one of two things will happen. Either I get to a feasible solution, in which case I'll get to an optimal solution. Feasible solution meaning that q is 0, a feasible solution to the original program, and get to an optimal solution. And then I can just throw this 0q variable out of my solution and I'll be done. Or it might be that I never managed to reduce q quite to 0, and that will be a proof then that the original program wasn't feasible. Okay? All right, so that's big M. So simplex now in one slide, skipping the last remaining point that I've been sweeping under the rug, which is handling degeneracies. It's going to be, you start with a non-singular standard form maximization linear program. And you start from a feasible basis, and it's Tableau, right? Big M, use big M if needed to get to a feasible basis, and it's Tableau. You then repeat the following. You pick a non-basic variable that has a negative, non-positive reduced cost. You pivot it into the basis, getting a neighboring basis. You select the exiting variable to keep feasibility. And you repeat, right? So repeat means going back to here. You keep picking something else to pivot in until you get to a point where everything that you could try and pivot in would wind up not helping your objective, right? And then you're done. Okay? So that algorithm makes sense to everybody? Okay. So, degeneracy. Degeneracy makes simplex implementations a lot more painful, but it's a fact of life. It turns out degenerate linear programs come up pretty often. And what is degeneracy? Well, not every set of M variables is going to lead to a corner, right? So some are infeasible. Some have rank less than M, meaning they're not a basis. So that's okay. The question is, can the reverse be true? Can two different bases yield the same corner? Right? Let's do a poll. Yes? Okay. No? Nobody's willing to bet against the rhetorical question. So can anybody come up with an example where two different bases lead to the same corner? Yeah. Right. We saw one earlier in the slides. You have 3 lines crossing at a single point in 2 dimensions. You choose any 2 of the lines, and it specifies that same corner. Right. Right. So here's an example, right? And so here's the original linear program, and here are 2 different bases that lead to the same corner, 8/3, 4/3, right? X and Y are in both of these bases, and then U or V completes it, and we get the same value for X and Y. Okay? So degeneracy in 3D. No glasses required, right? So if you take a look at, for example, this corner here, right, there are actually 5 different faces touching it, right? There's this one that's closest to the screen, this bottom one, the one that's farthest from the screen, and this top one, right? So there's 5 different faces touching it in 3 dimensions. That means that you're going to wind up with 5 choose 3 is 10 different bases that specify the same corner, right? And this shows you why degeneracy is common, right? This particular polyhedron, it doesn't look in any way special, but every single vertex of this polyhedron is degenerate, right? Which is kind of cool. All right, so we already looked at this, right? There were 5 constraints touching a vertex here. We only need 3 of them, so there are 5 choose 3 different bases, right? Are all of these bases neighbors of one another? How many people think yes? How many people think no? All right, we have no seems to win. Our voter turnout isn't very high. I hope it's better in the actual election. Right, so we have 5 choose 3, so we could choose the 1st, 2nd, and 3rd, or we could choose the 3rd, 4th, and 5th, right? And those aren't neighbors because they differ by two swaps, right? You'd have to swap, say, 1 for 5 and 2 for 4, okay? So they're not all neighbors of one another. And even though A and B are neighboring vertices of the polyhedron, they're not all neighbors of B, right? And so in general, if you have 2 vertices that are neighbors in the geometric sense, they're going to share at least one neighboring pair of bases, but it's not going to be the case that every basis for one is a neighbor of every basis for the other. Okay? So there's another type of degeneracy that we have to worry about for simplex. It's called dual degeneracy. I'm not going to say why it's called that, but you'll see pretty soon as Ryan starts lecturing. Suppose that we have in the objective row, we've ensured that all of our basic variables have reduced cost 0. We've removed them all from the objective because we want to think of them as slacks, and we can't put slack variables in the objective. But suppose that a non-basic variable has a 0 element, right, a reduced cost of 0. That means that adding it to our basis neither helps nor hurts, right? And so that means that basically when we move along the edge corresponding to this pivot, right, we're going to wind up not changing the objective. So if we have, for example, something like this, where the objective is orthogonal to one of the either edges or faces or hyperfaces, right, anything bigger than a vertex. If the objective is orthogonal to that, then there's going to be a dual degeneracy in which we can move along an edge without changing the value of the objective. Okay? And it might turn out to be valuable to do so because it might get us to a spot that has a much shorter path to the optimum vertex. Right? So we can't just rule out such pivots. So handling degeneracy, basically what that means is that in the simplex algorithm, sometimes we have to make pivots that don't improve the objective. And with ordinary degeneracy, that means that we stay at the same corner, right? This is ordinary, otherwise known as primal degeneracy. Or we move to another corner with the same objective, right? And what that means is that we have the problem of cycling, right? So if we allow ourselves not to improve the objective, then what's to prevent us from wandering along a bunch of vertices without improving the objective and then eventually getting back to where we started? And the answer to what's preventing us is an anti-cycling rule. And there are almost as many anti-cycling rules as there are pivoting rules, possibly more. The one that I like, because it's kind of conceptually nice, is, well, imagine that you add tiny random numbers to the objective and to the right-hand side, right? Then with probability 1, there are going to be no degeneracies. And so you're never going to have to worry about having a tie-breaking rule. Of course, you've changed the program, but if we make these random numbers really, really, really tiny, right, it turns out that we won't have changed it much. Right? And so won't have changed it much is actually formalizable, meaning that we can get from a solution of the new program to a solution of the old program. And so conceptually what we want to do is add, 10 to the minus 100 times rand n to the objective and the right-hand side. Of course, numerically that's a real bear. And so what people do is they try to achieve this same effect without running into numerical problems by some extra bookkeeping. So that's an example of an anti-cycling rule. And it's one that I kind of like because it's kind of similar to this idea that Spielman and Teng used to get a polytime simplex algorithm. All right. Yes? No. You can, for example, so the question was, if we detect a cycle, are we at optimum? And the answer is no. So if we, let's say that our objective was this way and we started at vertex A, right? We could wander among the 10 different bases for vertex A and have a cycle, but we definitely wouldn't be at an optimum, right? We have to wander among them and then eventually decide to leave this vertex to improve the objective. And obviously, just by looking at the polyhedron, we can tell when we're leaving the vertex, but it's not nearly as obvious to the simplex algorithm. Yeah. Go ahead. Seems easy to create what? Yes. The more dimensions you have, the more room there is to create degeneracies. Yes, absolutely. So, for example, if you select a whole bunch of random hyperspaces, random half planes, right? Random half spaces, right? If you do that, then with high probability, no more than d of them will intersect at any given point, right? And so, if you make that be your feasible region, then you're going to get a non-degenerate polyhedron. Yeah. So if all of your reduced costs are the right sign, right, not pointing. Let me think about. I have to think about that. Whether we can, maybe it'll be easier to answer that after we talk about duality. Right. Right. So the question was, how do you terminate? And I'll have to think about the answer. I don't actually remember it. Do you?
I'm sorry, how do you terminate in the degenerate case?
Yeah, in the degenerate case, how do you know, like if you're willing to move along edges with objective value 0, right? How do you know when you're done? Use duality. Yeah. Okay, so the answer is use duality and wait for Ryan's lecture, which is going to start in just a few minutes now, because this one is my last slide. I saw there was another question over here. That would be, I'm sorry? Right, this is dual degeneracy, is exactly when the objective is perpendicular to some edge. Oh, no, sorry, edge, face, anything, any d face for d bigger than or equal to 1. Yeah. It might be that you don't have any choices, right? You might have, so you can't certify that you're done by saying that, like if you forbid yourself from choosing any one of these variables, you might get stuck and not be able to choose anything. Right. Any more questions? All right, so let's take a brief break, and then when we come back, we'll start talking about duality.
We don't have much time left, but interesting connection between linear programming and duality. And I wanted to, well, we're going to start with duality and linear program, but I wanted to just kind of give a bit of historical recounting of why we're starting this way, besides the fact that it's a nice way to see duality. And so I told Jeff that the simplex algorithm was invented in 1937. I didn't know that off the top of my head. I was looking that up because the story is that Danzig invented the simplex algorithm.